The ideal gas law. Remember, ideally, an ideal gas will obey all of the gas laws perfectly under all conditions, kind of meaning it won't change state. There's no interactions. It has a zero volume, etc. However, we know that in reality, gases aren't all that ideal. And they won't always follow this kinetic molecular theory, i.e. we know that a gas will turn to a liquid if I cool it enough or I put it under enough pressure. I know that molecules have interactions like London dispersion forces, dipole-dipole, hydrogen bonding. I'm talking about molecules because, again, we don't have ionic compounds as gases, and we don't have network solids as gases either. We always have molecular compounds that have intermolecular force. And I know that particles take up space. So atoms obviously have a volume of some sort. So we could not compress even one atom to a volume of absolutely zero. So we can say that gases deviate or don't follow ideal gas behavior at low temperatures and high pressures. At low temperature and high pressure, remember, this is where a gas would start turning into a liquid. It's also where the particles are really close. Are close together. They are not moving quickly, not moving fast because they're at low temperatures. So, just kind of comparing a few of the assumptions for ideal versus real gases. Remember, we said that an ideal gas is a point mass. It takes up no space or volume, or has zero volume, but it has a mass. This is because the volume of empty space between particles is much, much larger than the volume of the particle itself. Okay, so if I have 3 particles in this space, the actual volume that this little dot takes up is so insignificant in comparison to the distance between these 2 particles that we could say that relatively this particle takes up no space in comparison to the space available within this box. However, at high pressures, the molecules of a gas become so tightly packed that their volume is significant compared to the overall volume of the box. Now, of course, I can't draw this quite as large, but the spaces in between these 2 dots is so small in comparison to the size of the dots itself that we start to say that these are starting to take up volume, and it's getting harder and harder to compress it to something at zero. Ideal gases travel in straight, constant motion until they collide with something like the container. The molecules do not have attractive or repulsive forces. So, in our container, this molecule is going to bounce off of the wall and travels in a straight line and travels in a straight line. No matter what other particles are in its way, it's going to keep traveling in straight lines after its collisions. However, what we know is that a real gas, as the temperature decreases, the molecules begin to slow down and have intermolecular forces. Because they're moving so slowly past one another, this molecule is moving so slowly that it starts to have an interaction, and it kind of dips towards that molecule. So it was traveling in a bit of a straight line, and then it's like, oh, there's somebody here, and I have a London dispersion, or a dipole-dipole, or a London dispersion force, and it becomes attracted to that molecule. It still has motion, so it continues on, but its path is no longer straight. So this can, cause it to not travel in straight lines, but if it is going slow enough, the momentum it has isn't enough to pull away from this molecule. and these two will become attracted to one another. If molecules become attracted to one another, and maybe more keep joining the party, they're starting to cluster. Clustered molecules are no longer gaseous. They don't have enough spaces in between them. So they become a liquid. So as I cool something, it cannot travel in a straight line anymore. So it starts to not travel in a straight path, to the point where it doesn't have enough energy to continue to pull apart from this other molecule that it had the attraction to, and it sticks with it. It has its intermolecular force, causing more of them to join, and it becomes a liquid. Once it's a liquid, I can't talk about pressure, temperature, and volume. They are no longer part of the combined gas law. We cannot talk about their properties as gases, so we cannot use these formulas. And the last thing is that ideal gases collide with elastic collisions. Having elastic collisions means that two molecules come together, and it's like they're marbles, for instance. Okay, they're very hard, they collide, and they completely rebound. They have not changed shape at all. Okay, so if marbles were able to be thrown at one another or the ground with great speed and not break, this is what would happen. So they do not kind of change shape. They are perfectly spherical the whole time. So none of their energy is used to convert their shape like we might be seeing over here. This is an elastic collision. All energy is conserved. And we know that this isn't the case in real life. Energy loss happens with every transfer. The interpretation for real gases is that real gas molecules change shape during a collision. They then rebound, and this process occurs a little bit more slowly. So these two molecules come towards one another and they collide. At their collision, the height of their collision, they have slightly deformed. Now, that is a change of energy. So we've seen that they have lost energy in changing their shape, and so they are going to rebound away from each other with less energy. So they come together with some sort of energy, 1, and their energy 2 that they leave, energy 2 is less than energy 1. And it's because some energy was lost in changing shape. Okay. This is an inelastic collision because energy is not completely conserved. Whereas over here, again, they come together with a particular energy and they leave with a particular energy, but E1 and E2 are equal. So, which of the noble gases will deviate from ideal gas behavior the most noticeably, and why? Again, deviate means not follow ideal gas behavior. So it's hard to talk about collisions because I'm not sure how to compare the compressibility of any of these noble gas atoms. So I'm not going to talk about collisions. I also don't really want to talk about them as a point mass. Because although I know that helium has 1 orbital and radon has 6, so radon is technically a larger atom. On the scale of atoms, this difference is not very large, okay? I mean, we can see it, but we would be measuring in like picometers, which are super duper duper small. So it's hard to compare when I'm looking at a box maybe or a volume of even 1 milliliter. The number of particles that can fit within there is still ginormous. So it's hard for me to understand that. Okay, so I'm not going to talk about a point mass either. Because again, the difference between the radius of helium and of radon, although it looks ginormous on here, is just insignificant in comparison, again, to the spaces between them. So what I am going to look at is I'm going to look at intermolecular forces and the attractions that these atoms have to one another. So noble gases aren't bonded to anything, and they are technically non-metal. So they're non-metals, not bonded. So they don't have any polarity. It's kind of what we're getting at. So noble gases, they have attractions based on London dispersion forces. So what affects the size of London dispersion forces? Because all of our noble gases, helium, neon, argon, krypton, etc., they all have London dispersion forces because they are all non-metals. They are not bonded to anything, and they just kind of exist as an atom. So the first thing that affects the size of London dispersion forces, or the strength of London dispersion forces, is the total number of electrons. Now, this is the total number of electrons in an atom, not valence electrons in the orbital, because technically all of these have, not helium, helium has 2. All of these have 8 valence electrons. So it's hard to compare. However, as I move down the group 18, the number of electrons increases. The number of total electrons, remember, is equal to the number of protons. So helium has 2 protons, helium has 2 electrons. Neon has 10 protons, neon has 10 electrons. Continuing on all the way down to the only other named element, we get to radon. Radon has 86 electrons. It's the most of all noble gases. So I'm not considering element number 118 una octum because it actually hasn't been discovered. Those are just placeholders. So radon has 86 electrons, the most of all noble gases, meaning that it has the strongest London dispersion forces, and therefore it has the strongest attractions of all the noble gas molecules, or atoms, sorry. So it will deviate from ideal gas behavior the most because it's the most likely to have stronger attractions to one another. So, to wrap it up, when are gases most ideal, or when are they most likely to follow the ideal gas laws? Well, this is when they have high temperatures because they're moving fast past other atoms / molecules. Okay, so they don't have time for intermolecular attractions. They are also most ideal at a low pressure. This is because with a low pressure, there is lots of space between molecules. Okay, so point mass still applies here. The spaces between them are so significantly greater than the volume that the atoms or molecules take up themselves. So gases are most ideal at high temperatures and low pressures. So now that we've done all of the theory about ideal gases again, we can take a look at the ideal gas law. So it's a mathematical relationship that describes the relationship of pressure, temperature, volume, and chemical amount into one equation. Okay? PV equals nRT is the formula, where P is, of course, pressure, V is volume, N is number of moles, R is new. R is something we need to look at, but T is temperature, and like in every equation so far, temperature must be in Kelvin. So what is R? R is the universal gas constant. Universal gas constant. It's on the back of our periodic table. It says that R is equal to 8.314 kPa per liter per mole Kelvin. That's what that unit stands for. So kPa times liters divided by moles times Kelvin. And that's just to cancel units. So these units here are telling me the units that everything else must be in. So because R contains units of kPa, pressure must be in kPa. Because R contains units of liters, volume must be in units of liters. Of course, we measure moles in moles itself. Don't forget that N is equal to little m over big M as a formula. And then, of course, we knew that T needs to be measured in Kelvin anyways. So they decided, experimented, to find this constant. It has more decimal places if you were to look up a more exact form, but this will do for our class. There are also other units. So we could look up R where it has units of atmospheres or millimeters of mercury. So we can change units of pressure. We just get a slightly different value here, of course, based on that conversion, that unit conversion. All right, so let's put this into practice. Example 1. Argon has many uses in refrigeration, lasers, and light bulbs. I think this was supposed to say neon. My apologies. Neon produces a red color when it is subjected to high voltage, which makes it, among other noble gases, useful in neon signs. What mass of neon gas should be introduced to an evacuated 0.88 liter tube to produce a pressure of 90 kilopascals at 30 degrees Celsius? Now, some of you may not understand what this means. An evacuated tube just means that it was totally empty. There was absolutely no gas molecules there until they added the neon. So we can guarantee that there's no oxygen, there's no carbon dioxide, no atmospheric gases present. It is simply neon. All right. I know that I'm using the ideal gas law here, and I'm not using combined gas law because there's no change in temperatures and pressures. There's no change in conditions here. I'm simply stating a set of conditions and looking for one property. So if that's the case, I'm looking at PV equals nRT. So I'm going to write out our variables. We have a pressure of 90 kilopascals and a volume of 0.88 liters. We don't know moles. It doesn't say it here. R is a constant. We always know this. 8.314 kPa liters per mole Kelvin. Big unit, but let's include it. And last but not least, we have a temperature of 30 degrees Celsius. Now remember, this needs to be in Kelvin. We're going to double check all of our units to make sure it matches with our units of R. So I add 273.15 and we get 303.15 Kelvin as a temperature. Checking the rest of my units, kPas, liters, moles would represent N, and K is Kelvin. Now we weren't asked for moles. We were asked for mass. But mass and moles are related, remember. So I can use my formula of PV equals nRT, and I can solve for moles. Once I have moles, I can use the formula N is equal to little m over big M to solve for mass. And that will answer my question. Because I can find moles through PV equals nRT, and of course I know what type of gas I have, I can use the this formula. All right, so let's get to it. Moles is equal to PV divided by RT if you rearrange your equation. So subbing in, I get 90 kPa. Again, don't forget to include units as you sub in. A number without a unit is not part of science. Okay, divided by 8.314 kPa liters per mole Kelvin, and times 303.15 Kelvin. When you put this in your calculator, absolutely make sure that there are brackets around what you are dividing by here. Otherwise, you are going to get a BEDMAS error in your number here. Your calculator will spit out a number, but it is not correct. All right, I calculated that N is equal to 0.0314237 moles. Now that's more significant digits than I need to write out. I don't need to write out my entire calculator here though. This isn't my final answer, so I want to keep some extra significant digits, but I don't need to waste time and write out every value in my calculator as we go through this. So looking at my question, I know that my final answer should have two significant figures. Therefore, in my interim answer, so not my final answer, just like a part ways answer, I need to keep my two significant figures plus one extra. Therefore, I, in the very least, should have rounded this to 0.0314 moles in the least to carry on with my final answer. I'll use what I have in green here, just because I've already got it written out. And although I'll probably use exactly what's in my calculator, I will write this as my interim. Okay, so continuing on to solve for mass, we have moles times the molar mass. The molar mass of neon is 20.18, and that is grams per mole. So taking that interim answer, 0.0314237 moles times 20.18 grams per mole, I'm just going to multiply what's in my calculator by 20.18, and I get a final answer of 0.63413, and that will be grams. Now, this isn't technically my final answer because I need to consider significant figures. We need to round to two significant figures. So 0.63 grams will be my final answer. So note that if I have been given mass or have been asked for mass, I'm going to use this formula as well as PV equals nRT because the moles can be related through these two formulas. Example 2. What volume does 50 kilograms of oxygen gas occupy in a gas tank that's at 50 atmospheres and 21.4 degrees Celsius? So I'm given a set of conditions. I'm not given changing conditions. Therefore, I know I'm using PV equals nRT. I have a pressure of 50 atmospheres. I'm looking for the volume. N, I don't have N. R is a constant. And temperature is 21.4 degrees Celsius. So we need to do some conversions. First, we need to convert our temperature into Kelvin. So adding 273.15, I get 294.55 Kelvin. I also need to convert pressure because pressure was given in atmospheres, whereas R tells me that pressure must be in kPa. So I'm going to take my 50 atmospheres, and I know that 1 atmosphere is equal to 101.325 kPa. So I'm going to multiply those two. Giant number here, I get 5,066.25 kPa to use in my equation. Now, if I were to write out PV equals nRT, at this point, I'm looking for volume, and I've got pressure, I've got R, I've got T, but I don't know N. And I can't solve for two variables in one equation. I have to just be solving for one. Therefore, what I'm going to do is I'm going to start with N is equal to little m over big M. I can find moles and change that from a question mark to a check mark. I just have to do one step first. So let's list out the values we need to calculate moles. We have a mass, which is 50 kilograms, and we need the molar mass of oxygen. Now, one oxygen atom has a molar mass of 16 grams per mole. However, in this case, remember, oxygen is diatomic. So the molar mass of oxygen gas is 2 times that, which is 32 grams per mole. Now, you can kind of see here, we have grams, whereas our unit of mass is kilograms. So we need to convert kilograms to grams. To do that, we multiply by 1,000, we get 50,000 grams. Let's sub into our formula. 50,000 grams divided by 32 grams per mole. I get 1,562.5 moles of oxygen. Now that I have that, I can sub that into this, 1,562.5 moles. Moles are in the correct unit here. Therefore, we are ready to solve for PV equals nRT. Volume is equal to nRT over P. So 1,562.5 moles times 8.314 kPa per liter per mole Kelvin times the temperature, which was 294.55 Kelvin, divided by pressure, which was 5,066.25 kPa. Now, we didn't look at this last time, but we can look at units canceling. Moles are on the top of a fraction here and the bottom here. Kelvin is on the top of a fraction here and the bottom of a fraction here. And I have kPa on the top of a fraction and the bottom of a fraction. The unit that my final answer will come out in is the only one not canceled, which is liters. Great news, because we're solving for volume. In the end, I calculated a volume of 755 liters. Now, technically, I need to have 2 significant figures. So, I'm going to round. I can't round without using scientific notation. So 7.6 times 10 to the 2 liters, or you can say 0.76 kiloliters. Up to you. The last example is a bit of an extension. If you are comfortable with ideal gas law so far, perhaps I would suggest you take a stab at questions that include density. If this is unfamiliar territory and it's not going as well, please don't fret. This is kind of your challenge question, and it's something you'd have to be able to answer to attain 100%, for instance, in this unit. So what is the density of argon at 20 degrees Celsius and 98 kPa? So I'm given a set of conditions, therefore I know that maybe PV equals nRT would be helpful here. So I have a temperature of 20 degrees Celsius and a pressure of 98 kPa, and R is a constant that we always have access to. So I don't have moles or volume. I know that moles is linked to this formula. And I know that density is mass over volume. Okay, that was part of our very first lesson. We talked briefly about density. So I have these 2 formulas that maybe I'd like to combine with my original PV equals nRT. So what I'm going to do is I'm going to take the moles formula and I'm going to sub that in for N, because I know that N is equal to little m over big M. I'm going to sub that right in for N here, PV equals, so instead of N, I'm going to put in N's formula. Okay. So this comes out to PV equals MRT over big M. Now, just to look at it a little bit nicer, I'm going to multiply both sides by big M to get it out of the denominator, and I get that MPV equals little m, RT, being careful about my capitals and not capitals, or lowercase, I suppose those would be called. All right, I still don't have density anywhere. However, I do have M and V. So let's go through and just check out what we do know. I can find the molar mass of argon. The molar mass of argon is 39.95 grams per mole. So in my equation here, I have big M, I have the value for P. I don't have V. I don't have M, but I have R and T. Now note that M and V both occur in the density formula. If I can arrange my formula to get M and V in the exact same position, so M in a numerator, V in a denominator, I can sub them out for D like we subbed in little m and big M for N. This is a little tricky. So what I'm going to do is I need to keep M in a numerator position. To do that, I'm going to move R and T to the other side then. So I get that little m is equal to MPV over RT. Now to get V in the denominator position here, I need to divide both sides by V. That cancels V here, and I'm left with M over V is equal to MP over RT. So we did a lot of rearrangement. What we did is we subbed in a known equation for a variable in another equation. We then rearranged the equation to find M over V, which I know is actually equal to density. So I can say then that density is equal to MP over RT. Whew. All right. From here, we should be able to solve our equation. Remember, 20 degrees is 293.15 Kelvin. All right, so density is equal to the molar mass, which was 39.95 grams per mole, times the pressure of 98 kPa, all over R, 8.314 kPa per liter over moles Kelvin, times 293.15 Kelvin. Again, don't forget to bracket these two numbers multiplying together if you're putting this into your calculator in one entry. I get a final answer of 1.606. Now let's try and figure out this unit. I have kPa in the top of a fraction, and it's going to cancel from what's down here. I'm going to be able to cancel Kelvin. I'm also going to be able to cancel moles. The only thing I get left with is grams and liters. We can figure out where they would be in the unit based on what we have as a formula, mass over volume. So my units for density should be the units of mass, which are grams, over volume. So my unit is 1.606 grams per liter. Final answer, we need to look at significant digits. In our question, there were 2 significant digits in each of these. So I'm going to round my answer to 1.6 grams per liter. This was tricky, again, because of this rearrangement to get the formula for density. There's some practice questions in your Nelson textbook on page 176 for the ideal gas law, as well as the theory that we covered at the beginning of this lesson.